Hey there, everybody. The topic is slope fields. Question 1. Consider the differential equation y prime equals 1 over x. Okay, that's just a derivative. Let's sketch a slope field for the given differential equation. Okay, so we're going to take this derivative. We're going to take ordered pairs. We're going to take the coordinates of those ordered pairs, the x and y coordinates, the x and y values, and everywhere we see x and or y, we're going to replace that number of that ordered pair in for the x or y in the derivative. So we're attempting to sketch a field of slopes using this derivative. All right, there's a lot of points here. So I guess just to be methodical, I might start at the origin. Think about the point 0, 0. 0 is x, 0 is y. Come up here to the derivative. The y's aren't going to matter because I have no y's in my equation. So my x-coordinate 0, that would require that I have 1 over 0, which is undefined. So at that ordered pair, I'm going to come over here and I'm going to sketch in a short slope segment through 0, 0 that's vertical. All right, now that I've made that observation that when x is 0, I'm going to be dividing by 0 in the derivative. So that means that anytime x is 0, which means you're on the y-axis, okay, you're going to get an undefined situation. So you'll have a vertical slope segment. So just looking at all these other ordered pairs here, I know on the y-axis I'm going to sketch in the short slope segment that's undefined. I guess I'm going to move now maybe to the right. So at each of these ordered pairs, I'm supposed to sketch in a little short slope segment that results from my evaluating that ordered pair in this derivative. Let's move over here to where x is 1. If x is the point 1, 0, or pardon me, if this point right here is 1, 0, x is 1, y is 0, okay, if I put 1 in for x, again, remember the y coordinates don't matter. If I put 1 in for x, the output is going to be 1. So at the point 1, 0, okay, I'm just saying that if 1, 0 is a point on the original graph, then the slope to that original graph, okay, would be 1. So through 1, 0, I'm going to draw a short slope segment that appears to have a slope of 1. Okay, now I'm thinking about other, structure here. If this point right here is 1, 1, where the x-coordinate is 1, and who cares about the y, my slope is also going to be 1. So through that point 1, 1, I'm going to draw in another slope segment that appears to have a slope of 1. So maybe the point 1, 1 is on the original graph, and if the point 1, 1 is on the original graph, then this would be the slope of the graph at that point on the original graph. So a lot of different situations. The antiderivative for this y prime could take on, a lot of different locations, if you will. All right, keep going up. All of these points along this column, or this vertical line right here, have x-coordinates of 1. And if the x-coordinate is 1, and who cares what the y is, it has no effect on the output of the derivative, okay, it appears that all of these slopes are going to be 1. So what we're doing is we're creating a column of parallel slope segments. All right, let's move over to where x is 2. This point is 2, 0. All that matters is when x is 2. So when we evaluate, we get 1/2. Well, thinking about how I'm going to compare that to this slope of 1, it's going to be less steep. And then think about all these points right here. All of these ordered pairs share an x-coordinate of 2. Who cares what the y is? So no matter which of these ordered pairs you plug into the derivative, your slope's going to be 1/2. So this entire column right here, if you will, this column, okay, will contain parallel slope segments of 1/2. Okay, let's move over to the right. X equals 3. This is 3, 0. So that slope becomes 1/3. It's going to be less steep than the previous slope of 1/2. And no matter what point you're on along this column, your slope's going to be 1/3. So this whole column right here will be have parallel slope segments. Less steep than the column before it. So as you can imagine, as you move to the right and the x values increase, well, in this derivative, my slope value is going to decrease, okay, to the point where perhaps when you're real far out on the x-axis, the slope is almost 0. It'll never be 0, but it's almost 0. So I'm trying to draw a column of parallel slope segments that are less steep than the column preceding this column. Okay, now I want to go backwards over here. Okay, let's think about x equals -1. Okay, at this point where x is -1 and y is 0, if I replace x with -1, my output's going to be -1. So through this point right here, I'm going to try and draw a slope segment of -1. And the same pattern results in this whole column. These are supposed to be parallel. All right, move over to where x is -2, so that means your slope is -1/2. It's less steep in a negative direction. So in this column, draw all the slopes of -1/2. The lines become, the slope segments become less steep the further you move to the left. Okay, we're creating a slope field. Okay, now on an AP test, I can tell you, you're not going to have to create a slope field with all these slopes. That shouldn't be horizontal. I've seen 12 or less points that they wanted you to calculate the slope at. Okay, and what does this slope field do for us, and what does it reveal? Well, the slope field reveals to us what the regular graph would look like, meaning what the original, the antiderivative, what y would look like. Okay, so it gives us an idea of the shape of the graph. And we'll look at that in some other parts of this problem. So this is a slope field using this derivative. Some things to take away. Because my derivative only has x, think columns, think x equals, then I'm going to have columns of parallel slope segments. Okay. All right, let's look at part B. All right, B says let y equals f of x be the particular solution. So it's just saying that this derivative does have a regular equation. Let y equals f of x, whatever that is, be the particular solution. The antiderivative once we found c. Remember, when your original function has a plus c, that's still called a general solution. But a particular solution means that we've actually gone through and found the c value. So it's important to pay attention to the words and what they mean we've done. So y equals f of x is the particular solution to this differential equation. Okay, with initial condition. Well, you guys know this is initial condition. This is a point on the regular graph. Then it says draw a solution curve through this point. A solution curve means draw a picture of the original function that contains the point 2, 3. So easy enough. Let's go and find 2, 3. 1, 2, 1, 2, 3. Okay. So what we do know is that this is the derivative, and a point that's on the regular graph is 2, 3. What we're going to do is we're going to use the slopes that we've created to suggest to us what the regular graph would look like. So here's the rule of thumb. From this point, this initial condition, travel to the right and travel back to the left. All right, when I travel to the right, I'm guided by the direction, if you will, of the short slope segments. So maybe it comes off here with the slope of whatever this was, 1/2, but as I travel to the right, the graph is going to be less steep. Show your arrow. All right, come back to the initial condition. We want to draw the rest of the graph to the left of this ordered pair. Well, the slope suggests that I'm going to continue down this way. And notice right here that these vertical slopes right here, or vertical segments, if you will, okay, indicate there's probably an asymptote. So it looks like my graph is going to continue downward this way. So I'm being guided by these slopes. I'm following the direction of those slopes. And if you think about this graph right here, it's a natural log graph. It's a logarithmic graph. And the connection here is this. You might have already seen it. Well, some of you might remember that if this is y prime, that this is the derivative, 1 over x is, of some natural log function plus c. It just so happens that they told me the plus c was going to be the ordered pair 2, 3. So then I just have the natural log graph off of that point. So sometimes you're asked to do that. You're asked to sketch a slope field, and then based on the observation of the directions of the slopes and given an initial condition that you're going to plot, you're going to just extend the graph to the left and right following the direction of the slopes. Okay, the hardest part of this unit, this unit of slope fields, is probably going to be part C. Okay, it's not going to be that difficult in this first example, but by the time we get to the third example, it's pretty intense algebraically. All right, so let's take a look at part C. Find the particular solution. Now it's saying actually go back and find the equation of the original function. Okay, given this point. And we've done this before. We've integrated, plugged in a point, found C, and then reported what the regular graph is. So for us, this one's not new. It's just it's a revisitation of an old skill. But let's go ahead and do an easy example, because by the time we get to the third example and it's more complicated, we're going to be glad we have the structure. Okay, so maybe over here somewhere in the space provided, we're going to do part C. Okay, what we did in the past to get back to y is we separated the variables, so to speak. We left the dy, we pulled over the dx. Okay, notice we're dividing, so over here it's going to become a multiplication situation. Okay, what we did is then we brought in an integral symbol on both sides of the equation. The antiderivative, okay, here is going to be y. We'll leave the plus c for the right side of the equation. Okay, now it's up to us to do some integration. Well, we remember that 1 over x is the antiderivative is the natural log of the absolute value of x plus c. All right, have I completed the objective of finding the particular solution? No, actually, I've just found the general solution. If they ask me just to find the general solution, I'm finished. But because they gave me an initial condition, likely they're going to ask me to find this c value. And what we did in the past, if you remember, 2 is x, 3 is y. We replace those values in here, and we solve for c. All right, the absolute value is not necessary here because the 2 is already positive, so you could drop the absolute value. To solve for c, I'm going to subtract the ln2. So now I know what my constant of integration is. So coming back, writing the equation without the c. Okay, I know it's kind of weird. Plus 3 minus ln2. But all of this collects to a constant. Okay, this right here is my particular solution because I found c. So I've completed the task. All right, let's take a look at example 2. So I'm sure you've already noticed that this derivative, y prime, contains a y and not an x, not both. This might be a good time. If you flip over the worksheet, look at the back, look at number 3 on the back. That given derivative has both x's and y's. And I want you to think about it as we create the slope fields for these, how they compare, how they're the same, how they're different. All right, so for number 2, let's sketch a slope field. Okay, so I'm going to go ahead and start with the origin. That's just a good starting place. The ordered pair is 0, 0, 0 for x, 0 for y. Now this time x's don't matter. The only thing that matters in the ordered pair I select from the coordinate plane is the y coordinate. So y is 0, add 2, so the slope is 2. So at the origin, I'm going to try and draw in a slope of 2. So then I begin to think, okay, well, if every y is 0, that means I'm on the x-axis. Okay, every y is 0 no matter what the x's are because we discard those. They're not necessary. If every y is 0, my slope will always be 2. So instead of columns, I'm going to have rows of parallel segments. I'm attempting poorly to draw a slope of 2 across this row. So that tells me that I'm probably going to be looking at rows and looking for patterns. So now maybe go up and say, okay, along this row, every y coordinate is 1. Who cares what the x is? Every y is 1. When I add that to 2, I get a slope value of 3. So if any of these points right here fall on the antiderivative, the regular graph, the slope of the graph would be 3 at these points. Okay, now go up. If y is 2, no matter what x is, my slope would be 4. Okay. Well, these can't be vertical because I'll never have a vertical slope. It's poor. But they're going to be more steep vertically than the preceding row. So some observations. If all I have in my derivative is y, then I'm going to have rows of parallel slope segments. This might be a good time to fall down a little bit. When y is -1, that means we're here. If the y values are -1, and I add 2, I'm going to get 1. So comparison to the previous row, the row above it, it should be less steep. All these slope segments should be less steep. Okay. If y is -2, means I'm along this row. If y is -2, my slopes are 0. So it looks like I have a horizontal tangent. If the graph of the regular function passes through any of these points, it looks like there's going to be a horizontal tangent. Or maybe a horizontal asymptote. All right, let's go down to where y is -3. That means my slope is -1. So it's going to go in the opposite direction. All right, so if I'm along this row right here, y is -4, then it looks like I'm going to, be at -2? So it looks like it's going to be more steep. So based on the previous example, try and attempt to do part B on your own. This is a good time to pause the video and draw your solution curve through the given point, and then turn the video back on and check it. All right, if you kind of check your work here, you can see that when you start from the point 1, 2, that would be on the antiderivative, it appears that the further up you go, the graph becomes pretty steep. Now, when you come back down off of this point, you can see that your graph is kind of bending this way. I didn't mean to touch the asymptote here, but the slope suggests that I have a horizontal asymptote right here. So the graph would continue off. And if you think about this particular function right here, if you think about it, it's an exponential function. So I'm kind of suspicious about this derivative that was given. I'm thinking, well, this must be the derivative of an exponential function. So in part C, where it asks me to find the particular solution, it's asking me to integrate, go back and find the original graph. I'm thinking I'm going to get an exponential equation. Okay, the actual process of finding this solution, instead of them just saying let or consider f of x to be the particular solution, when it says find, that means there's going to be some work. And for this particular one, it's going to be a little more involved than the previous one. And by the time we get to example 3, the algebra is going to be even more involved, and it'll be one of the hardest ones that you're asked to solve. Okay, so for part C, we're going to find the particular solution that has this initial condition. All right, so we're going to find the particular solution to this differential equation. So it's going to require a lot of room, so I'm going to start the problem over here. Okay, for this particular problem, it gets a little strange. We're going to pull the dx over to the other side by multiplying both sides. And when you think about it, you've got quantity y plus 2 with the differential. Well, y needs to be on its side, which is on the left side. So to get y plus 2 to the other side, I would divide both sides of this equation by y plus 2. So the result of that would be dy over y plus 2 equals dx. So what we did is we just thought of this as an entire expression, divided it out from the right side, and then multiplied the dx onto the other side. All right, so this is where we're at. Let's bring in the integral symbol. Okay, we can do u substitution here. U is y plus 2. The derivative would be dy. So doing u substitution, hopefully you guys can see that dy gets replaced with du. Y plus 2 becomes u. Okay, we have a little more work to do. I'll do that in my next step. The antiderivative here is x. Okay, x plus c. I'm going to try and work to the left a little bit because I think I'm going to need a little more space here to the right. The antiderivative here would be the natural log absolute value of u, which was y plus 2, equals x plus c. My suggestion at this point is let's find the value of c. I haven't completed this problem yet. I haven't solved for y equals. It's not in y equals f of x form yet. Okay, I'll take care of that in a minute, but let me find c by using the initial condition 1, 2. So this is x, this is y. So natural log of absolute value of 2 plus 2 equals x is 1, 1 plus c. Natural log of 4 equals 1 plus c. So my c value is what? Natural log of 4 minus 1. But you could simplify 4 to 2 squared and pull the 2 in front, but totally not necessary. Okay, natural log, absolute value, y plus 2 equals x plus, the c value is natural log of 4 minus 1. Okay, trying to pay attention to the time here. I know I'm talking a little bit fast, but if you need to kind of like stop, pause, and then go back and turn it back on, that might be a good thing. Okay, at this point, you're nearly finished. This is a great place to be. The last thing you want to do is exponentiate both sides because I want to get y by itself. So if I bring in e to both sides of the equation, I take this entire side and raise it as an exponent. Okay, and then here, I know these two undo each other, so I'm left with absolute value of y plus 2 equals, okay, and this is going to throw some students off here, but what I want you to think about is I'm going to separate the variable part. I'm going to say it's e to the x times e to the ln 4 times e to the negative 1. All of these exponents, because I have the same base, would be added and it would give me back to this place right here. So this is just a property from Algebra 1 with exponents done backwards. Okay, so just kind of pause, think about that, process it. So absolute value of y plus 2, a little cleanup, e to the x. Okay, this would simplify to 4, and then 4 times 1 over e, because that's what this is. So it's really times 4 over e. Okay, and so almost done. What I want to do is I want to remove the absolute value. Well, when I remove the absolute value, I have to remember that I might have a positive or a negative solution. So removing the absolute value, I don't know what that is. That absolute value shouldn't be there. Y plus 2 equals positive, negative, and I'm going to put the 4 over e in front and times that by e to the x. Now I can't cancel these two right here because this is e to the x and e to the first. So this shouldn't be here. Okay, so as a final step here, let's subtract a 2. So negative 2 plus or minus 4 over e times e to the x. That's the name for this function right here. Well, it's only one of them. It's not the plus and the minus. So how do we figure out which one it is? Well, I'm going to go back to the initial condition, and I'm going to figure out by plugging in 2 for y. Okay, and what? 1 for x. This is 2, negative 2 plus or minus e, 4 over e, times e to the first here. Now notice that I can cancel the e's now. I know this is quick. You might have to pause it. Okay, cancel these here. So now I've got 2 equals negative 2 plus or minus 4. Well, think about the only one that's true. Is negative 2 minus 4 equal to 2? No. Is negative 2 plus the 4 equal to 2? Yep. So I know that 2 has to equal negative 2 plus the 4. Otherwise, the other one wouldn't match up. So what root is it? It's going to be the positive. I say root, but which value is it? It's the positive one. So coming back up here, my answer, or maybe over here, okay, is that y equals negative 2 plus 4 over e times e to the x. Okay, so I'll see you in the next video.